So for the second part here of week 4, we're going to look at some of these special probability distributions. And we're looking mostly at the discrete ones this week. We'll come back next week and look at the continuous distributions, the normal distribution. For right now, let's look at examples of these discrete distributions. Let me get everything working here, right? Now, the way I've got this set up now, in order to be able to access my calculator, I've got to be able to switch back and forth. So this is going to shut our animations off here for a second. But here we have, suppose we decide to record the gender of the next 25 newborn babies at a particular hospital. Examples here of questions that we could ask. What is the chance that at least 15 are female? What is the chance that between 10 and 15 are female? Or out of the 25 newborns, how many can be expected to be female? These questions can all be asked of something called the binomial distribution. Binomial distribution has some special characteristics. So properties of binomial distribution. There are a fixed number of trials. Now this textbook doesn't use this terminology, but there's something called a Bernoulli trial. A Bernoulli trial has one of two outcomes, success or failure. Now that doesn't mean there's only two outcomes, but the outcomes can be divided in those two categories. You know, flipping a coin, we might label heads a success, tails a failure. Rolling a die could still be used. We might label getting a 1 or a 2 a success and everything else a failure. So it's not just two outcomes, it's that they can be divided into those two events or two categories of a success or failure. Each trial results in one of two mutually exclusive outcomes. That's what we were saying, success or failure. Outcomes of different trials are independent. So just like flipping a coin, we could flip heads 10 times in a row. The probability of getting heads on the next flip is still 1 out of 2 or 0.5. Probability that a trial results in success is the same for all trials. So that probability does not change. If we had, threw marbles in a box, drawing out those marbles, well, every marble we draw out, unless we put them back in, the probability changes slightly. So that would not be binomial. If we put them back in and mixed them up after every draw, then it would still be a binomial situation. So in the binomial probability distribution, the random variable x is the number of successes observed in a set number of trials. So for the binomial experiment, we set the number of trials. So n is the number of trials. Let's say we're going to flip a coin 10 times. N equals 10. There's 10 trials there. That's our experiment. P is the probability of success on each trial. So again, for flipping that coin, if we defined heads to be a success, P would be 0.5. That's the probability of having a heads on each individual trial. And X is the number of successes out of those N trials. Oops. Okay, so it won't let me bring back my animation there. No big deal. So are these binomial distributions? Are each of these a binomial situations? If we toss a coin 10 times and count the number of heads, yes, that is binomial. Because again, n equals 10. We've tossed the coin 10 times. P, probability of 0.5. That one's assumed here from the coin. And yes, x is the number of heads. That is our random variable out of those 10 trials. Deal 10 cards from a shuffled deck and count the number of red cards. This does not quite meet it because if we deal out the 10 cards, we're not putting them back. If we flipped out a card, if we drew a card, recorded whether it was red or not, then put it back, that would be binomial. But here we're just taking out 10 cards at once. That's not binomial because if the first card's red, that changes the probability that the second card could be red. So it's not quite binomial. The probability does not remain constant, exactly constant from one trial to the next. 3, the number of tickets sold to children under 12 at a movie theater in an hour period of time. This is not binomial because we're not controlling how many children there are. If we said the number of tickets sold to children under 12 out of the next 100 customers, that would be binomial. But saying an hour's period of time, we don't have a set number of trials there. So the formula for binomial probabilities, oops, not what I wanted. The probability of success, or of a certain number of successes, I should say, where n is the total number of trials, x is the number of successes out of those trials, and p is the probability of success on an individual trial, is n factorial over x factorial. Now factorial, 4 factorial, remember, is 4 times 3 times 2 times 1. That's what that factorial notation means. We can find these values in the tables at the end of the book in Appendix 5, or in the appendix, Table 9 is the one we're looking for there. Technology such as calculators can also help us do this. I'm going to show you how to use the TI-84 to calculate these binomial probabilities as well. Almost never use the formula for those binomial calculations. So instead of recording the gender of the next 25 newborns at a particular hospital, let's record the gender of the next 5, just to make the calculation a little bit simpler. Is this a binomial experiment? Yes. The births are independent. We're going to assume there's no twins born. Maybe we should have said excluding twins. Gender is independent. Gender of one baby born should not affect the gender of the next baby born. And the probability should be about the same. It's not exactly 0.5, but we'll assume it is for this example. Define the random variable of interest. Well, the random variable here, n is 5, we're taking the next 5 newborns. X is the number of females born out of those next 5 births. So X can take on the values from 0, 1, 2, 3, 4, or 5. So the binomial random variable always includes 0? It really should. And then the largest value of the binomial random variable will change, of course, the situation, but that largest possible value of x will always be equal to n. And of course, our probability of success here, we're assuming it's 0.5, even though in reality, slightly greater chance of having a female child than male. Okay, so here, what is the probability of exactly 2 girls? Now, it's very important here that it's exactly 2 girls. So that means the probability that x equals 2. So we're doing that 5 choose 2, and then 0.5. Now, I'm going to show you where this comes from. The 5 choose 2, remember, is 5 factorial over 2 factorial, 5 minus 2 factorial. The 0.5 squared, that's p to the power of the number of successes, so p to the x. The 0.5 here, that's actually 1 minus p to the power of n minus x. The 3 is we have 5 trials and we want 2 girls, so 5 minus 2 is 3. 1 minus p, if the probability of having a girl is 0.5, 1 minus 0.5 is also 0.5. So that's where those numbers come from. So we calculate that all out. I'm going to pull up the calculator here. Change my viewing window here for just a second. Pull my calculator into the window so we can see what's going on. Oops, get back here. There we go. So I have that 5 factorial on the TI-84. You do 5, then you go to math. Probability. Oops, probability. This factorial is option 4 there. That calculates the 5 factorial. Now I have to divide by 2 factorial. 2 factorial. Then I also have to divide by 5 minus 2, which was 3 factorial. Giving us 10. So 5 choose 2 here. This 5C2 is 10. Luckily, the calculator actually has a built-in function for 5 choose 2. Could have entered 5, go to math, probability. See, option 3 is NCR. Well, 5 is N, that's the total number of trials. Oops, let me clear this out. Something went wrong here. Let me try that again. So 5, math. Option 3, NCR. 2. And notice we get 10 for that value. Then we multiply by 0.5 to the power of 2 times, oops, I gotta, careful there. In this calculator, once we do a power, we gotta make sure we do the arrow to get out of that power, times parenthesis 1 minus 0.5 to the power of 5 minus 2. So that's actually using just the long form of the formula instead of the abbreviated form they used on this slide. Notice we get that 0.3125 that they got here. The calculator, by the way, has a built-in binomial probability function. So we can do the second key here. Above the VARS key is distribution, D-I-S-T-R, stands for distribution. The binomial distribution is way down the line here. There's 2 of them, binomial PDF and binomial CDF. Binomial PDF is binomial probability distribution function. That would be if we want exactly 1. So here we have exactly a certain value. Where we have exactly 2 girls, that's the one we want. So we're going to select that. We have 5 trials, so we're doing 5 babies. P, we're assuming 0.5 probability. And we want to know the probability of 2 of them being girls. Gives us 0.3125. So we get the same probability with all of those different methods. Now the second example here is slightly different. What is the probability that less than 2? Now you got to be careful with the wording there. It says less than 2. So X is less than 2. That does not include the 2. That's only the 0 and the 1. So we have 2 probabilities. We have to find the probability of 0. That's 5 choose 0, 0.5 to the 0, 0.5 to the 5. So 5 of them would be boys. And the probability of 1 of them being girls. That's 5 choose 1, 0.5 to the 1 for the girls, 0.5 to the 4 for 4 of them being boys. Now, I'm going to assume you guys can enter this calculation in the calculator, going back and following that previous example. Just to do the first part here, the 5 choose 2, remember it's 5, math, probability, PRB, NCR, 0, if that's 5 choose 0. Gives us there's only one way to select 0 out of 5. You just don't take any of them. Times 0.5 to the power of 0. And then times 0.5 to the power of 5. We get 0.03125. The other one, of course, is going to give us 0.15625, I believe, is what that comes out to be. But you can calculate that second part out yourself just by substituting into that process. I'm going to go ahead about how do we use this on the calculator? Well, we could do each of those separately on the calculator if we wanted to. Second, distribution. Binomial PDF, 5 trials, 0.5, let's 0 girls out of that. Gives us that 0.03125 like we said. Go back to that distribution. Still 5 trials, still 0.5 probability of success, but only 1 girl now out of them. That's the 0.15625. We add those together, we do get the 0.1875 that we got here. There is a way we could do this all at once on the calculator. There's the binomial CDF function. Binomial PDF was binomial probability distribution function. Binomial CDF is binomial cumulative distribution function, which means we add up from 0 up to that number. Now this is less than or equal to 2, which means we don't want the 2. So we're going up to 1. So when I enter this in the calculator, second, distribution, arrow all the way down to option B, which is binomial CDF. So I'm still asked for a number of trials, 5 trials. Probability of success on each trial is 0.5. Now I want to go from 0 to 1. I don't want the 2. The 2 is not included. And we notice there it is, the 0.1875. So newborns continue. Let's construct the distribution table for this probability, for this situation. So the probability of 0, we already found that on the calculator. That's the 0.03125. We found the probability of 1, 0.15625, and we found the probability of 2, so we have to find the probability of the others. Now you'll notice this distribution is symmetrical. The probability of 3 is equal to the probability of 2, the 4 is equal to the 1, the 5 is equal to 0. The reason that's symmetrical is because p equals 0.5. So the probability of being a girl is the same as the probability of not being a girl. So that means the probability of none of them being girls is the same as the probability of all of them being girls. If p is not, that only occurs if p is 0.5. If is any other probability other than 0.5, it will not be symmetrical like that. So you cannot assume they'll be symmetrical. Most cases they will not be. What is the mean number of girls born in the next 5 births? So again, the mean, you take each value times its probability. 0 times 0.03125, that's 0. 1 times the 0.15625, that's right there. 2 times 0.3125, and on down the line. We add those up and we get 2.5. Now there is a shortcut formula for this that we could have done using our parameters x, n, and p. We find that the expected value, or the mean, of a binomial distribution is just the number of trials times the probability of success. Looking back here, n was 5 trials times p of 0.5. That gave us 2.5. And then our standard deviation is the square root of n times p times 1 minus p. So for this situation, n was 5, p was 0.5, 1 minus p will be 1 minus 0.5. The square root of that, the square root of 5 times 0.5 times 1 minus 0.5 is just 0.5. Gives us 1.118. So we can see the calculation worked out here. So remember, in binomial distributions, trials should be independent. So the result of one trial should never have any effect on the possibility of the results of the next trial. However, when we sample, we typically sample without replacement. So like we said, taking the cards out of the deck. We didn't put the first card back before we draw the second card. That's without replacement. That affected the probabilities. So trials are typically not independent. So in this case, if the trials are not independent, we use something called the hypergeometric distribution. So the hypergeometric distribution allows for that non-replacement. So the trials are not independent. So that's the big difference between our binomial distribution and this hypergeometric distribution, is the trials are not independent of each other. But when the sample size n is small and the population, capital N, is very large, the probabilities can still be calculated with the binomial distribution, because while the probability changes, it's not enough to really make a difference. So if we have a really large population and a really small sample, the results from binomial distribution and the hypergeometric distribution are very, very close to the same. So the calculation for probabilities in the hypergeometric distribution are even more tedious than the binomial. They're a little bit longer formula. And again, the sampling without replacement, if it's less than, the sample is less than 5% of the population, we can stick with the binomial distribution then. So the actual formula for the hypergeometric distribution is given here. Don't worry, you won't be asked to do it as a graded portion of the class, but I wanted to throw it out there. So probability of having x successes out of n is the sample size, or the size of the population, m is the number of successes in the population, and n is the size of the sample, is m choose x, capital N minus m choose little n minus x, over capital N choose little n. So let's do an example here. The example I want to do is, let's say you're going to draw those 10 cards out of the deck. So out of a 52 card deck, I want to find the probability that exactly 4 will be spades. So now for this case, x is 4, little n is 10, we're drawing 10 cards, capital N is 52, and m is the number of successes in the whole population. There are 13 spades in the whole population. So our probability that x equals 4 will be, m, we have 13 spades. We're going to choose 4 of them. I'm going to use a little bit more familiar notation. So 13, choose 4, times n minus m. So n minus m leaves us with 39. Choose n minus x, 10 minus 4, there's 6. So what this is saying here is we want to choose 4 of the 13 successes and 6 of the 39 that are not successes. And of course, this will be divided by 52, choose 13. So on the calculator, let's do that. So we've got 13, math, choose 4, times 39, math, choose 6, divided by 52, choose 13. Gives us a 0.0367. So 0.00367 or 37, we're going to call that. So that's less than a 1% chance that 4 out of those 10 cards, it's actually a 0.37% chance that 4 out of those 10 cards will be spades. So that's how the hypergeometric function works. Now for this class, the hypergeometric function is, like I said, a little more complex than we want to do for this class. So we're going to talk about something called just the geometric function, geometric probability. Not hypergeometric, just geometric. So we're going to revisit this problem. Suppose we're not interested in the number of females born out of the next 5, but we're only interested in how many children are born before the first one is female. So notice this is slightly different. The binomial distribution had a set number of trials. We were looking at 5 babies, and we wanted to know how many of them would meet the qualification. Here, we're looking at how many babies are going to be born before our qualification is met for the first time. That is a geometric distribution. So there are 2 mutually exclusive outcomes that result in success or failure, just like with binomial. Each trial is independent. So this is how it differs from the hypergeometric. In hypergeometric, the probabilities change a little bit from one trial to the next. In geometric, the probability stays the same. And that third qualification, the probability of success is the same from one trial to the next. So that's how this is different from the hypergeometric. The geometric random variable x is defined as the number of trials until we hit the first success. So it could be 1, the first baby, and it includes the success itself. The first baby could be female, so that would be 1. And it could go up to infinity. We could have baby after baby that were all male. Very unlikely, but it's possible. So there isn't a limit to the geometric random variable. So this would go up to infinity. And of course, those possible values of x always start at 1. 0 is not a possibility in the geometric distribution. So our formula is simply 1 minus p to the power of x minus 1 times p. This is the probability of a success. This is the probability of having x minus 1 failures before that success. So, suppose that 40% of students who drive to campus at your school carry jumper cables. Your car is a dead battery, you don't have jumper cables, so you're going to ask students coming to the parking lot if they have a pair of jumper cables. So x is going to be the number of students you have to stop before you find one with jumper cables. This is definitely a geometric distribution. So, first question, let the number of students stop before finding one pair of jumper cables be our x. P is 0.4. What is the probability that the third student will be the first one that has jumper cables? So the probability that x equals exactly 3. Well, 1 minus 0.4 is 0.6. That's the probability that they will not have jumper cables. So 0.6 to the power of 2 is saying the first two don't have jumper cables. This 0.4 here then is the probability of success for the third one, giving us probability of 0.144 is the probability that third student will be the first one that has jumper cables. Next, what is the probability that at most 3 students are stopped before you find one? So now we're going to add probabilities. This one is saying that the first one has jumper cables. So there's 0 failures, that's the 0.6 to the 0, and the 1 success. Plus the probability that the second one has jumper cables, so there'd be 1 failure followed by the 1 success. Plus the probability the third one has jumper cables, so that's 2 failures followed by 1 success. And we'd add those up. So there's a 0.784, or over a 78% chance that if you've asked 3 students, that at least one of them is going to have the jumper cables. So that within the first 3 students, you're going to find somebody who has jumper cables that can help you out. So that is the geometric distribution. Now I want to move on to another distribution. This one is not in the book. So I'm going to close down the PowerPoint here. This distribution is another discrete distribution called the Poisson distribution. The Poisson distribution talks about the number of successes we will have in a given period of time. So, couple of things about the Poisson distribution. Sometimes it's used if there's just an extremely large number of trials and a very low number of successes. It can be used kind of in place of the binomial distribution. More often it's used when we know an average number of successes out of a given amount or a given period of time. But we have 2 parameters that we use for the Poisson distribution. The first parameter is lambda. That's the Greek letter lambda. And that stands for the mean number of occurrences in a given period of time. So the mean number of occurrences in the desired length of time. In other words, the expected value in that period of time. And then R is the desired number of occurrences. Now there's also in this formula is going to be the letter E. Remember, E is a natural constant. So the formula for that probability is the probability that X equals R. In other words, that we have R occurrences in this given period of time is E to the power of lambda times or sorry, e to the power of negative lambda, I should say, times lambda to the power of r divided by r factorial. So let's look at some examples of this. So our first example. Let's say that a manufacturing process has a 0.2% defect rate. So that's that very low probability of success. We're in this case kind of awkward, but we're assuming that a defect is a success. So very low probability of occurrence here. I want to find the probability that exactly 8 out of the next 5,000 parts have a defect. So here we've got r is going to equal 8. The total 5,000 doesn't become a parameter, but it does affect lambda. Lambda 0.2% is going to be 0.2% of that 5,000. So 5,000 times 0.002 giving us 10. So 10 is our lambda. That would be what we'd expect to be the average number of defects out of those 5,000 parts. So our probability that x equals 8 here is going to be e to the negative lambda, so e to the negative 10, times lambda 10 to the power of r, so that's 8, over 8 factorial. So on our calculators to get e, we got to see ln here. Above it has an e to the x, so it's second ln. That's e to the x. Enter negative 10. Arrow to the right to get out of my exponent there. Times lambda of 10 to the power of 8. Once again, I arrow to get out of that. Divided by 8 math factorial. Giving us 0.11259, so we're going to round that to 0.1126 is that probability. So 0.1126 is the probability that exactly 8 out of the next 5,000 parts is going to have a defect. So that's an example where we have a large number of trials, 5,000 parts, and a very low probability of success. The other possibility, again, is if we're not necessarily looking at trials, but we're looking at volume of a certain item. So this example would look like this. Let's say the average Wisconsin road, I live in Wisconsin, so that's why I'm using this statistic, in the spring has 3.2 frost heaves per mile. In the spring, our roads get busted up as the frost comes out of the ground. So we're going to find the probability of 10 frost heaves, of exactly 10 frost heaves. So put that term in there, exactly 10. So no more nor less. On a 4-mile stretch of road. So here R equals 10 frost heaves. Lambda is going to be 4 miles times 3.2 frost heaves per mile. That comes out to 12.8 is the average number, the expected number of frost heaves in that 4-mile stretch. So our probability, our Poisson probability here, that x equals 10 is going to be e to the power of negative lambda, so to the negative 12.8, times lambda, 12.8 to the power of r, so the power of 10, divided by 10 factorial. So again, second ln gives us the e to the power of. Use the negative key there, negative 12.8. Arrow out of there. Times 12.8 to the power of 10. Arrow out of that power, divided by the 10. Math. Factorial. Equals 0.0898. So that probability of having exactly 10 frost heaves in that 4-mile stretch of road is just under 9%. So that is the Poisson distribution. Again, that's not in the book, but we covered a little bit in some of the homework. So that is all the material for this week. If you have any questions, please let me know and I'll get back to you as soon as I can. Otherwise, have a great week.